Major of the United States Air Force, Robert Cardenas, looks into the eyepiece of the Norden optical bomb sight. Before him lies a mathematical grid meant to guide the bomber onto the target from an altitude of several thousand feet. Yet the crosshairs twitch from side to side, as if in fever. Beneath Cardenas's feet, there is no familiar long fuselage. Behind him, there is no heavy tail assembly. The cockpit is built directly into the leading edge of the giant airfoil. Right behind the crew, inside the metal mass, the turbines roar, generating such levels of vibration and thunder that after every flight, the test pilots step onto the concrete with temporary deafness. 194,000 pounds of aviation aluminum, filled with high-octane fuel and shaped like an enormous boomerang, glide through the cold air over the Mojave Desert. This is the Northrop YB-49 bomber, a machine that arrived 42 years ahead of its time. And a machine that proved absolutely, fundamentally useless at its sole task, dropping bombs in a straight line. The central mystery of this multi-million-dollar project reads like a cruel engineering joke. Why did an aircraft with perfect aerodynamic efficiency, freed from the dead weight of a fuselage, kill its crew and bury its own production simply because the engineers removed a component considered indispensable since the start of the century? By the mid-40s, classic military aviation had run into a physical ceiling. Piston engines gulped thousands of gallons of gasoline merely to drag cigar-shaped fuselages through the dense layers of the atmosphere. The fuselage produced no lift. It produced only parasite drag. The heavy tail added weight and slowed the aircraft. Engineers wasted colossal engine power trying to overcome the air resistance generated by the airframe itself. Jack Northrop, founder of the aircraft company, viewed the classic layout as aerodynamic junk. His math was cold and precise. If the fuselage and tail assembly were cut away, leaving only the lifting surface, drag would fall by half. This promised double the range or bomb load for the same fuel burn. The United States military, urgently needing an intercontinental carrier for the new atomic weapon, wrote the check. The requirement was rigid. Deliver the nuclear payload across the ocean and return to base. Initially, the project was built under the index XB-35 and equipped with piston engines, but the complex gearboxes of the coaxial propellers constantly failed from vibration. Then the Army Command ordered the propellers cut away, and the two unfinished airframes converted to the latest jet turbines. The wingspan of the new prototype measured 170 feet. The surface area totaled 4,000 square feet. On this slab of aluminum, 24 modern passenger cars could have parked with ease. Inside the solid wing, Northrop engineers installed 8 Allison J-35 turbojet engines. Each engine delivered 4,000 pounds of thrust. Together they produced 32,000 pounds of force, the equivalent of a dozen heavy railroad locomotives pushing a monolithic metal slab through the atmosphere. The aircraft accelerated to 493 miles per hour, leaving its piston rivals far behind. On paper, the drawings and graphs looked like an unconditional victory over gravity. The problem was that static graphs ignored the brutal dynamics of real airflow. A classic heavy aircraft holds a straight course thanks to the vertical fin mounted on the long lever of the fuselage. The tail acts like the fletching of an arrow, damping yaw. Jack Northrop removed the tail for the sake of conceptual purity. In the early piston version, the role of aerodynamic stabilizers was forced upon the enormous counter-rotating propellers. When those propellers were removed and replaced with smooth jet exhaust pipes, the wing lost its final aerodynamic support about the yaw axis. Major Cardenas wrote scathing lines in his reports. Without a tail, the multi-ton machine constantly and unpredictably yawed left and right. The Norden optical sight required rigid alignment with the aircraft's structural axis. For an unguided bomb to strike a strategic factory on another continent, the crew had to hold a perfectly straight course for several minutes before release. The YB-49 could not fly a straight line for even 10 seconds. The smooth wing had become an uncontrollable pendulum. The attempt to introduce the aerodynamics of the future ran aground on the computing technology of the 40s. To make the unstable airframe fly straight, electronic computers were required that could read sensor data dozens of times per second and control the surfaces through a fly-by-wire system. But in the cramped compartment there were no processors, only living men, whose muscles and the primitive analog gyroscopes of the autopilot could not cope with the laws of physics. This technological chasm rapidly drove the project to a boiling point, turning the advanced bomber into an aluminum mousetrap. The engineers of Northrop Aircraft Incorporated found themselves squeezed between the laws of physics and a rigid contract. To save the multi-million-dollar project, they made a compromise that destroyed the very idea of the pure wing. Trying to damp the lateral rocking, the designers bolted 4 small vertical fins to the trailing edge. The aerodynamics were ruined. A complex mechanical hydraulic yaw damper was integrated into the control system, a cumbersome arrangement of valves meant to sense the aircraft's deviations and counter them with the rudders faster than the pilot could. But the hydraulics of the 40s responded with fatal lag. The airplane wallowed in the air while the loads on the frames during the surges grew exponentially. Captain Glenn Edwards, the Air Force's most experienced test pilot, hated this ergonomics. Wedged into the narrow glass greenhouse at the leading edge of the airfoil, he physically felt the vulnerability of the concept. Directly behind the armored back of his seat whirled the turbines of 8 Allison engines. The roar made the intercom useless. Vibration from the nozzles traveled through the aluminum structure straight into the bones. 5 men sat inside a hollow blade slicing the atmosphere at nearly 500 miles per hour. Later, a myth would arise that the YB-49 had become the first stealth aircraft. During flights, ground radars did indeed lose the machine from their screens because the rounded leading edge scattered radio waves. But Captain Edwards knew the price of that invisibility. It was an accidental side effect. Antennas protruded from the wing, the 4 fins created corner reflectors, and the incandescent exhaust of the 8 turbines glowed so brightly in the infrared spectrum that the aircraft could be detected without radar. The real problem remained simply keeping the multi-ton structure in level flight. The point of no return came on June 5, 1948. The second prototype, serial number 42-102368, lifted off from Muroc Air Base for routine stall tests. Glenn Edwards and his crew were to determine how the wing behaved at the loss of speed. In a classic aircraft, when the airflow stalls, the heavy nose drops, the machine gains speed, and lift is restored. But the aerodynamics of the flying wing concealed a fatal flaw. When the Northrop wing lost speed, the center of pressure shifted sharply forward. Instead of lowering the nose, the aircraft did the opposite. It uncontrollably pitched the leading edge upward. This phenomenon is called pitch up at the stall. Without a long tail lever, the pilot had no mechanical tool to bring the nose back down. The multi-ton bomber reared up, exposing nearly 4,300 square feet of wing to the oncoming flow at hundreds of miles per hour. The overload appeared instantly. The pressure of the incoming air struck the lower skin with a force exceeding the calculated strength limit of the spars. In 1948, there were no flight recorders. The final seconds were recorded only by the metal itself. The conclusions of the official Air Force board stated, "Structural failure in flight. Pilot error ruled out." The aircraft killed Glenn Edwards and 4 other crew members with its fundamental physics. The extreme load tore the primary structure apart. both outer wing panels separated from the center section right in the sky. The mangled central section crashed north of the dry lake, scattering dozens of tons of aluminum and burning fuel across the Mojave Desert. Muroc Air Base would later be renamed Edwards Air Force Base, forever recording the price of this experiment. The death of the crew was only a catalyst. The true executioner of the project was cold economics and the geometry of nuclear weapons. After the crash, Northrop continued to persuade the Pentagon of the layout's promise, but the numbers did not add up. The switch from piston engines to jet turbines consumed the aircraft's chief advantage: range. 8 Allison engines burned so much kerosene that the combat radius fell below the critical threshold needed to strike Soviet territory. It was a strategic bomber that physically could not reach its strategy. The second problem was even more primitive. The United States nuclear arsenal in the late 40s consisted of Mark III Fat Man bombs. These were monstrous spherical assemblies with a plutonium core more than 5 feet in diameter. The flying wing concept assumed that the payload would be hidden inside the streamlined airfoil, but the thickness of the YB-49 center section was simply insufficient to close the bomb bay doors around the dimensions of the atomic weapon. To carry such a weapon, it would have had to be hung externally on pylons, which would instantly destroy all the aerodynamics. The competitor was Convair, with its B-36 Peacemaker bomber. It was an unwieldy, gigantic 6-engine aircraft with a classic fuselage that looked like a relic of the past. But the B-36 possessed an enormous bomb bay that could freely accommodate any existing nuclear weapon and could loiter for days in the cold air, crossing oceans. The military arms market chose not the elegance of advanced drawings, but the crude utility of a capacious aluminum cylinder. Many years later, a conspiracy theory circulated in the aviation press that Secretary of the Air Force Stuart Symington had ordered the aircraft destroyed out of personal revenge. Supposedly, Jack Northrop had refused to merge his independent company with Convair, and the enraged secretary had sent the unique wings to the scrapyard. Declassified archives proved this was only a consoling myth for the defeated enthusiasts. The military simply refused categorically to pay millions of dollars for a bomber that could not accurately drop bombs, could not carry a heavy atomic weapon, could not reach another continent, and mercilessly killed its own pilots. In November 1948, the government contract was finally canceled. On March 15, 1950, the surviving first prototype was performing high-speed taxi tests. During the run along the concrete, the nose landing gear could not withstand the severe lateral oscillations and collapsed with a deafening crunch. The 80-ton machine pitched forward onto the runway. The duralumin structure broke in half, and thousands of gallons of high-octane fuel poured from the ruptured tanks. Fire consumed the company's pride within minutes. The pilot miraculously escaped, but the revolutionary project burned to the ground. The last remaining airframe, of the reconnaissance variant, stood at the back of the California plant for another 3 years, until in 1953 it was cut into pieces. The huge sheets of shining skin were sold for scrap at the price of cheap industrial waste. The era in which ambitious engineers tried to outwit aerodynamic instability mechanically, without the help of digital computers, ended with the whine of circular saws and the dry signatures of army accountants. On February 9, 1949, Northrop's chief pilot, Max Stanley, flies the surviving first prototype of the YB-49 bomber over the continental United States. It is a demonstration flight from Muroc Air Base in California to Andrews Air Force Base. 8 Allison turbojet engines push the airframe to maximum cruising speed. The coast-to-coast distance is covered in a record 4 hours and 25 minutes. On the runway at the airbase, the aircraft is personally met by President Harry Truman. He inspects the smooth duralumin skin, admires the futuristic profile, and instructs the press to report on the triumph of American engineering. But inside the cramped cockpit, hidden in the leading edge of the wing, Max Stanley and his crew feel not pride, but physical exhaustion. The record dash across the country came at the price of a continuous struggle with the heavy control yokes. The Honeywell autopilots installed on board had analog architecture and primitive mechanical gyros. They responded to changes in attitude with a delay of fractions of a second. For an ordinary bomber with a long fuselage and large fin, this reaction speed was sufficient. But the smooth-flying wing slid through the airflows with such unpredictable frequency that the analog automation only aggravated the oscillation, attempting to compensate for deviations that had already passed. The pilots had to take control themselves. For 4.5 hours, the men worked as biological yaw dampers, tensing their muscles to keep the multi-ton machine on course. Behind Stanley's seat, the temperature of the structure reached critical levels. 8 scorching jet pipes were located right inside the wing, forcing the engineers to fight thermal expansion of the metal and the risk of fire in lines laid centimeters from the turbines. The demonstration for the president was a grand illusion, masking an engineering dead end. The company founder, Jack Knudsen Northrop, faced a harsh mathematical fact. His perfect aerodynamic concept destroyed the practical value of the bomber. The absence of a fuselage meant that all usable volume had to be squeezed into the thickness of the wing airfoil. In the 1940s, the United States possessed Mark III nuclear bombs. These were massive steel spheres, more than 5 feet in diameter, filled with a complex system of lenses made of conventional explosives that compressed the plutonium core. When the engineers tried to integrate the weapon into the drawings, they discovered that the height of the weapons bay was less than the diameter of the bomb. The doors would not close. For the YB-49 to carry the only weapon for which it had been created, the bomb would have to be suspended externally, ruining the ideal streamlining and catastrophically reducing speed. Military analysts calculated the operating costs and range with the new jet engines, and the figures were devastating. The total thrust of 32,000 pounds of force consumed kerosene at such a rate that the strategic bomber could not reach the borders of a potential enemy and return without refueling. The competitor from Convair, the unwieldy giant B-36, with 6 piston engines, had ugly aerodynamics, but its enormous fuselage held tens of tons of fuel and bombs of any size. The generals of the United States Air Force made the pragmatic choice. Aerodynamic elegance did not matter if it could not deliver a nuclear weapon to the target. Jack Northrop tried to prove that the wing airfoil could be thickened, that new alloys would solve the heat dissipation problem, but the board of directors looked only at the cost tables and the reports on instability during the bomb run. The final pages of the project's history were written not in design offices, but on scrap heaps. After the contracts were canceled in November 1948, the Air Force lost interest in preserving the unique airframes. By 1953, the last surviving example, the reconnaissance prototype designated YRB-49A, had been towed to the edge of the airfield. An order from the Department of Defense required the complete scrapping of the aircraft. Workers brought up tractors and began cutting the metal. Jack Northrop came in person to watch the destruction of his dream. He saw heavy industrial guillotines and hydraulic shears crushing the aluminum spars, whose calculations had cost his engineers hundreds of thousands of man-hours. The machines shredded 370 square meters of skin, turning perfect aerodynamic surfaces into piles of broken scrap. The vertical fins, installed in a desperate attempt to save directional stability, flew off under the blows of sledgehammers. The complex mechanical damping system, consisting of miles of hydraulic tubing and valves, bled hydraulic fluid onto the dusty ground. The metal from which they had planned to forge air superiority was sold by weight for a pittance. This was not an act of bureaucratic revenge, as enthusiasts would later like to write. It was a ruthless sanitary pruning of a dead-end branch of evolution. The aircraft had outrun the computing power of its era by half a century and was destroyed for its inability to function in an analog world. Northrop left the aviation industry a broken man, convinced that his concept had been buried forever by the short-sightedness of generals. He did not live to see the moment when the development of silicon processors changed the rules. Only in 1989, exactly 42 years after the YB-49 first lifted off the concrete, did the B-2 Spirit bomber rise into the sky. Externally, it looked like an exact, blackened copy of Northrop's old machine. The same 170-foot wingspan, the same absence of a fuselage, the same pure blade without tail surfaces. The laws of aerodynamics had remained unchanged, but the mechanics of control had changed. Where Max Stanley had fought the yoke to exhaustion, and Glenn Edwards had entered a fatal dive, a fly-by-wire system took over the work. The B-2's onboard computers read angular rate and pressure sensors hundreds of times per second. The digital brain continuously and imperceptibly deflected tiny split ailerons on the trailing edge, creating artificial drag on one half-wing or the other. The aircraft remained fundamentally unstable. It still tended to slip or pitch up, but the processor countered those tendencies before they could develop into real loads, translating the chaos of physics into flight as straight as a string. Technology had advanced far enough to replace the missing tail with algorithms. The development cost of the B-2 exceeded tens of billions of dollars, proving that stabilizing a flying wing required a budget comparable to that of an entire nation-state. The irony of reality is that the engineers of the 1940s were absolutely right in their drawings, but cruelly mistaken in the materials and technologies of their time. The aluminium slab, unable to fly without a digital brain, killed the first test pilots and ruined its creator in order to become the most expensive and deadly weapon of the next century. Secretary of the Air Force Stuart Symington sits at a massive oak table in the Pentagon, studying a dry financial report on operating costs. Before him lie graphs of kerosene consumption and comparative tables of combat radius. Symington is not an engineer. He is an administrator, and he is interested in only one metric: the cost of delivering a single nuclear bomb to the territory of a potential enemy. In 1948, that cost for the Northrop project fell outside any budgetary sense. Originally, the piston-powered predecessor, XB-35, had been conceived with a calculated range of 10,000 miles. That was enough for a transoceanic flight, but when the Army Command ordered the installation of Allison J-35A-15 turbojet engines, the project's mathematics collapsed. 8 jet pipes demanded a colossal volume of fuel, yet inside the thin wing there was simply no free space for additional tanks. Every 100 gallons of kerosene displaced hydraulic lines and equipment. The YB-49's range fell by half. The aircraft had become a strategic bomber that could not leave the borders of its own continent without aerial refueling, a technology then still in its infancy. Symington looked at the drawings of the smooth wing and saw not an aerodynamic triumph, but a financial black hole. To save the contract, Jack Northrop and his chief engineer tried to cheat physics mechanically. When Major Robert Cardenas proved the machine's absolute unsuitability for precision bombing because of its lateral oscillation, the designers installed a mechanical hydraulic yaw damper. The device consisted of an intricate labyrinth of duralumin tubing, bypass valves, and massive gyros integrated directly into the center section structure. It worked like this. When the wing yawed, Involuntarily, left or right, the heavy gyro rotor deflected, physically pushing a metal rod. The rod opened the spool of the distribution valve, and hydraulic fluid at hundreds of atmospheres of pressure rushed through the lines to the hydraulic cylinders at the wingtips. The cylinders extended special split-drag rudders, creating aerodynamic resistance and straightening the course. On paper, the scheme looked brilliant. In reality, the hydraulics of the 40s possessed fatal inertia. From the moment the gyro deflected to the actual deployment of the surfaces, fractions of a second passed. At a cruising speed of 420 miles per hour, those fractions of a second meant the aircraft had already wandered farther off course while the automation began correcting a position that was no longer current. The damper entered resonance with the airframe's aerodynamics, rocking the 80-ton structure even more violently. Test pilots were forced to overpower the automation physically, twisting the yokes until their knuckles turned white. The engineering department spent hundreds of thousands of dollars calibrating the valves, but overcoming hydraulic lag without digital processors proved impossible. In a desperate attempt to save the company from bankruptcy, Northrop offered the military a conversion of the bomber into a long-range reconnaissance aircraft. The project received the designation YB-49A. To recover the lost range, the engineers made a decision that destroyed the very essence of the flying wing concept. Since there was not enough room for kerosene inside the smooth airfoil, they moved 2 of the 8 turbojet engines outside, suspending them in large nacelles beneath the center section. The remaining space inside the wing was filled with fuel tanks. The external engines and their mounting hardware created enormous frontal drag. The ideal aerodynamic cleanliness was lost forever. What had been conceived as a radar-invisible blade became an unwieldy monster hung with metallic growths. The reconnaissance variant flew, yet its performance proved even worse than that of the original bomber. Maximum speed dropped, and vibration from the external engines transmitted into the structure, rupturing the thin seams of the fuel tanks. Kerosene began seeping directly into compartments containing hot pipelines. Crews had to fly in constant expectation of a massive fire. The customer, the United States Air Force, refused to fund further work on this engineering death throw. Meanwhile, at Convair's plants, B-36 Peacemaker bombers were being assembled at full speed. These were colossal machines, with classic cigar-shaped fuselages. They were ugly, sluggish, and equipped with temperamental piston engines that mechanics called a maintenance nightmare. But Convair has 2 indisputable advantages that cannot be beaten by any aerodynamic formulas. The first advantage is a gigantic bomb bay, with a volume of hundreds of cubic meters, into which armorers freely load thermonuclear charges of any shape. The YB-49, with its thin wing profile, physically could not accommodate even the standard Mark III atomic charge without its sticking out. The second advantage, the colossal payload capacity and tank volume of the B-36, allowed it to loiter in the air for days on end. It could take off from bases in the United States of America, pass over the North Pole, drop its load on the industrial centers of the Soviet Union, and return. Northrop's flying wing would have crashed into the ocean halfway due to lack of kerosene. The economy of the Cold War always prefers a crude, working sledgehammer to the most elegant but useless scalpel. The verdict of the market is final and not subject to appeal. Symington places his signature on the document for the complete cessation of funding. The Air Force Accident Investigation Board confirms that the machines are structurally unstable. No conspiracy by competitors exists. There is only dry bookkeeping and the laws of aerodynamics, which Northrop's engineers attempted to leap over without the corresponding technological base. The factory halls in Hawthorne fall into silence. The unfinished airframes of the piston-powered YB-35 versions and the jet prototypes are hauled to the back lot. These are tens of millions of taxpayer dollars embodied in high-alloy aviation aluminum, precision bearings, and miles of copper wiring. In 1953, the military department issues a dry order. Clear the parking areas. Caterpillar tractors and industrial hydraulic presses are brought in. Heavy machinery cuts through the primary frames with milling cutters, rips the Allison turbojet engines from the wings, and crushes the smooth skin into shapeless briquettes. The 80-ton structures, whose wing area totaled 4,000 square feet, collapse under the blows of steel buckets. Jack Northrop resigns from his own company and leaves the aviation industry forever, crushed by the sight of his brilliant mistake being sold at scrap metal prices for a few cents per pound. The perfect aerodynamic machine, decades ahead of its time, perished not in combat and not at the hands of saboteurs, but under the blow of an impartial accounting report that proved the future could not be built on the analog technologies of the present. In April 1980, the founder of the aircraft corporation, Jack Knudsen Northrop, sits in a wheelchair in his hospital room. He is 84 years old, suffers from a severe illness, has lost the ability to speak and move independently, and his former company has long operated without his involvement. Engineers from a special advanced projects division with a classified budget arrive with a cardboard box. A representative of the United States Air Force Command obtains special permission to partially disclose a state secret to this man. From the box, they extract a heavy wooden model of a future strategic bomber that 9 years later would receive the official name B-2 Spirit. Northrop lifts the model with weakened hands and runs his fingers along its precisely shaped leading edge. He cannot utter a single word aloud, but on a prepared sheet of paper, he writes a short phrase, saying that now he knows why he has lived so long. Beneath his palms lies an exact geometric copy of the YB-49. The same calculated wingspan of 170 feet, the same uncompromising absence of a fuselage, the same complete absence of a vertical tail. 32 years after the moment when industrial hydraulic presses tore the duralumin skin of his creation to pieces on a California scrap heap, the Pentagon invests tens of billions of dollars in the very same aerodynamic shape. But between the wooden model in the hands of the old aircraft designer and the real combat aircraft of the late 20th century lies an insurmountable technological gulf, filled not with aviation metal, but with complex computational algorithms. The cruel mathematical irony lay in the fact that the concept of an absolutely clean flying wing never belonged to the world of crude analog mechanics. When in June 1948, Captain Glenn Edwards desperately fought the jammed mechanical hydraulic yaw damper, he was vainly pitting his muscular strength and the pressure of hydraulic oil against chaotic aerodynamic instability. This physical battle had already been lost by the engineers at the drawing board stage. To make a colossal monolithic surface fly a straight bomb run, the next generation of designers had to discard steel control cables, aluminum pulleys, and heavy hydraulic valves forever. Northrop Grumman engineers installed a quadruply redundant digital fly-by-wire control system in the new B-2 Spirit project. Inside the ultra-strong carbon fiber body of the latest bomber, there is no direct mechanical connection between the pilot's yoke and the movable control surfaces. Every movement of the military pilot's hand is instantly converted into a digital electronic signal. Powerful onboard computers continuously read precise data from external sensors of attitude, dynamic pressure of the cold air, and angle of attack hundreds of times every second. Silicon processors ceaselessly calculate a mathematical model of the aerodynamic instability and send short electrical pulses to the servos. Tiny split ailerons on the trailing edge deflect by mere millimeters at superhuman speed, creating the necessary artificial drag on either the left or right half-wing. The computer physically prevents the multi-ton aircraft from entering the deadly pitch-up that tore apart the YB-49 over the Mojave Desert. The digital computational algorithm completely replaced the missing vertical fin. What Jack Northrop had tried in vain to solve with 4 square meters of additional duralumin and impossibly heavy mechanical gyros, the engineers of the 80s elegantly solved with silicon microprocessors, weighing only a few grams. The financial statistics of this engineering solution proved to be truly merciless. If the entire YB-49 development program cost American taxpayers several tens of millions of dollars, an already astronomical and prohibitive sum for the post-war budget, then the cost of just one production B-2 Spirit strategic bomber exceeded $2 billion. To enable the smooth aerodynamic wing to drop a thermonuclear bomb stably and accurately required colossal government investment. The very same famous Norden optical sight, through whose crosshairs Major Robert Cardenas had vainly tried to hold an aiming point amid the wild shaking of the unstable airframe, gave way to powerful synthetic aperture radar systems integrated directly into the composite skin. The old Allison J-35 jet engines, which deafened the crew with unbearable noise and burned aviation kerosene with the efficiency of an open forest fire, were replaced by modern General Electric turbofan engines tucked deep inside the structure to cool the hot exhaust and radically reduce the infrared signature. The metal of the old YB-49, whose countless rivets and crude weld seams reflected enemy radio waves like a giant mirror, was entirely replaced by classified radar-absorbent composite materials. The basic aerodynamic physics for which officials had mercilessly destroyed the first prototypes remained absolutely untouched. The absence of a heavy fuselage and tail still provided enormous lift and incredible stealth. In the 40s, humanity simply lacked the necessary tools to tame that physics. The remnants of that very first aviation metal, from which this brutal engineering evolution was painfully forged, disappeared without a trace long ago. After the military bureaucrats issued the final scrapping order in 1953, the pieces of the cut-up aluminum airframes were promptly sent to steel mills. The high-grade aviation duralumin was melted down in ordinary furnaces. It is entirely possible that from the shining skin of the bomber that had so phenomenally outrun its time, ordinary kitchen pots, cheap construction profiles, or parts of inexpensive civilian automobiles were stamped. Tons of the most complex, high-precision instruments, expensive gyros, and many miles of high-quality copper wiring simply rotted on dirty industrial scrap heaps. All that remained of the ambitious program were several dozen grainy motion picture films showing the giant metal boomerang sliding over the dry salt lake, and a few thick cardboard folders containing dry technical accident reports carefully preserved in the dusty archives of the United States Air Force. Those classified reports recorded the deaths of the pilots and the catastrophic structural failure of the metal with remarkably cold, bureaucratic precision. No one in the Pentagon mourned the lost aesthetics of the smooth wing. The free market and rigid military doctrine demanded reliable, guaranteed delivery of heavy plutonium spheres to the target, and Northrop's innovative machine could not even guarantee its own structural integrity while performing a simple maneuver in calm air. The YB-49 project remains forever in the history of military aviation as the harshest lesson in engineering timing. Cold technology absolutely does not tolerate premature human ambition. If a designer deliberately removes a critically important stabilizing element from a complex mechanical system in order to reduce drag, he is morally obligated to replace it with something far faster and mathematically more precise than human reflex and a sluggish hydraulic valve. Jack Northrop's machine was an absolutely perfect aerodynamic differential equation, in which only one vital variable was critically missing: a high-speed digital computer. Without that key variable, 87,969 kilograms of premium alloy aluminum were mathematically doomed to become the most expensive, deadly, and pointless engineering mistake of its decade. 4 long decades later, the complex equation was finally solved, and the unstable flying wing became the deadliest strategic weapon on the planet. This proved beyond any doubt that in the combat aviation of the future, there is absolutely no place for primitive mechanical compromises. To outrun one's own time by a full half-century in reality means only one thing. You will design and build a magnificent mechanism that your pragmatic contemporaries will inevitably cut up into cheap scrap metal, simply because processors capable of safely holding this colossal weight in the air have not yet been invented in their laboratories. Major of the United States Air Force Robert Cardenas places the final signature on the classified test report. On his desk lie not sketches of future wings, but dry tables of vibration loads, telemetry of airflow separation, and graphs of aviation kerosene consumption. Cardenas is the pilot who survived inside the cramped cockpit of the Northrop YB-49, and it is his testimony that drives the final steel nail into the coffin of this project. In his technical conclusion, he records the ultimate verdict with merciless directness. The flying wing is fundamentally unsuitable for performing the tasks of strategic bomber aviation. This is not an opinion. It is documented physics. Cardenas describes in detail how at an altitude of 33,000 feet, the Allison turbojet engines gasp in the thin air, losing thrust, while the complete absence of a vertical tail forces the 80-ton machine to yaw continuously across the horizon. The amplitude of the oscillations makes holding the Norden optical sight's crosshairs an impossible task. To compensate for the turbulence, the pilots must manually wrestle the heavy yoke, causing constant deflection of the massive elevons on the trailing edge. Each movement of the surfaces creates additional aerodynamic drag that instantly bleeds off speed and forces the turbines to burn precious fuel. This is a vicious engineering cycle from which no mechanical exit existed in the 40s. Beyond Cardenas's office walls, the armament service engineers attempt to solve an insoluble spatial puzzle. Strategic Command rigidly demands that the aircraft be capable of delivering a production Mark III atomic bomb to the target. This is a monolithic steel sphere, weighing 10,300 pounds and measuring 60 inches in diameter. The architecture of the smooth wing dictates a ruthless rule. All usable internal space is trapped between the upper and lower duralumin skin of the center section. When the ordnance officers measure the maximum height of the YB-49's internal bomb bay, they run into a dead mathematical wall. The thickness of the airfoil measures just over 3 feet at its deepest point. The giant steel sphere physically will not fit inside the bay. If an attempt is made to close the lower bomb bay doors, the metal bomb pushes them outward. The designers of Northrop Aircraft Incorporated propose a compromise. Hang the nuclear weapon externally, directly beneath the smooth underside. But the combat officers understand perfectly well that placing an almost 5-ton sphere outside the clean airfoil will completely destroy the aircraft's primary aerodynamic advantage. The increased frontal drag will reduce the already critically shortened range imposed by the jet engines to unacceptable levels. The machine will not cross the ocean, even one way. While Northrop's experimental prototypes burn government budgets on futile attempts to cheat the laws of dynamics, Convair's production lines are assembling a competitor that looks like a massive mockery of elegance. The B-36 Peacemaker bomber is a colossal aluminum tube 49 meters long. It has an incredibly long fuselage, a huge vertical tail, and 6 piston engines, to which 4 more jet turbines will later be added. The design is entirely devoid of revolutionary ambitions. Its indisputable advantage is crude utilitarian capacity. The bomb bay of this unwieldy monster has a volume of 340 cubic meters. It swallows not 1 but 2 Mark III atomic bombs without difficulty, closing its doors tightly. The thick wing panels hold tens of thousands of gallons of high-octane aviation gasoline, guaranteeing a range of 10,000 miles. The accountants in the Pentagon do not pay millions of dollars for pure aesthetics. They are buying the assured mathematical probability of delivering destructive energy to another continent. Inside the B-36 cockpit, there is no deafening roar of incandescent turbines directly behind the bulkhead, and the tail provides the stability needed to hold the multi-ton machine on a straight bomb run.